So our next speaker is from Penn State University, where it's so warm and sunny that here in Toronto he has to wear a big heavy coat. I know exactly how you feel, so it's a pleasure to introduce Satwata, who'll speak on scalable operators with coefficients in a C-star algebra.
Thank you for the introduction, Nigel. I am Satwata, and thank you for the opportunity to give me to talk here at the Fields Institute. So today I'll be speaking on scalable operators with coefficients in a C-star algebra. And what basically I'll be talking about is this new modern theory of pseudo-differential calculus due to Eric Van Erp and Robert Yanken. This is a more geometric approach to pseudo-differential operator theory. And at a later point, we'll talk about how we have extended this to a setup with operators with coefficients. And all of this is partly based on a question with representation theory. So to get down to business, I'll start with the motivation from representation theory. Just a small disclaimer that this might be a little heavy on representation theory. If that is not your taste, it does not matter. The heart of the content really does not depend on this. Okay, so to get down to business, I'll start with a recent result of Nigel and Peter DiBello. What they are saying is that if you take a connected real reductive group G and a compact maximal subgroup K, there's a natural isomorphism from the representation ring of the compact subgroup K to the K theory of a certain C-star category. The C-star category is basically contains all kinds of order 0 pseudo-differential operators on the symmetric space of G acting on the right on K. So it's like a huge category of all possible order 0 pseudo-differential operators, and the vector bundles kind of arise from the representations, finite dimensional representations of K. Now this isomorphism they have got is equivalent to the Kohn-Kasparov isomorphism, and just from this one has a natural question that one wants to understand this order 0 operators or order 0 equivariant operators better from a representation theoretic perspective. So that's the question we are trying to get towards. Now again, Nigel and Peter have made a head start on groups of real rank 1. So what they have shown is that for groups of real rank 1, there is an isomorphism for order 0 equivariant operators on the left. This does not work. So order 0 equivariant operators on the left to a certain space of functions. So these functions are like, so this AP, you are looking at the domain of these functions are like rank 1, so dimension 1 vector space. That's where the real rank 1 comes, and they're like operator valued equivariant or matrix valued equivariant functions. Okay. So a basic instinct is to generalize this kind of a result for groups of higher real rank. To make a modest start in this exercise, I want to ask that what happens if G is a group of real rank 2. And let's consider some examples. Let's say SL2R cross SL2R or SL3R. So if I just consider SL2R cross SL2R, it somehow feels necessary from a representation theoretic perspective that one needs to really tweak with the operator algebra on the left, the algebra of order 0 pseudo-differential operators. One need to tweak with that. And from a representation theoretic perspective, again, one feels that the right operators to study here is operators of tensor product type. Now, what are these operators? These operators are kind of operator valued operators on each copy of SL2R. So they decompose as operator valued operators on each copy of SL2R. Now, if one goes back in time, like a long back in time in 1980s, Mischenko and Fomenko studied this class of operators called like operators with values on Hilbert C-star bundles and such kinds of operators to generalize the Atiyah-Singer index theorem. So our goal today is to like poke at this question of operator valued operators from the perspective of Van Erp and Yanken. Okay. So to introduce this Van Erp-Yanken calculus, I would first talk about certain phenomena one can observe using very simple calculus basically of linear partial differential operators. So let's start with a linear partial differential operator of order P. I cannot really use the pointer, so just the P is there, the highest order part. And I would be considering rescaling operators. So these operators basically rescale your input of the functions by a positive scalar lambda. And now if I consider certain family of operators, which we get by conjugating the operator d with this rescaling business, and with an additional factor of t to the power p, which the p again comes from the order of the operator, coordinate-wise calculation gives me such a thing. This is not very interesting, but hold on. If I take the limit t goes to 0, I get something very nice. I recovered the principal part or the top order part of the differential operator with frozen coefficients at t equals to 0. So what I get is that this family of operators I started with extends smoothly at t equals to 0 to this principal part operator with frozen coefficients. So the picture of that is, if I start with the operator at d, in a intermediate value between 0 and 1, I have like two kinds of parts, one of the lower order parts and one of the highest order part. The blue is the highest order part. Now if I take it to t equals to 0, only the highest order part survives, everything else is killed away. So there's a deformation of my operator d to the principal part. This is the phenomena I want to capture, or Van Arp and Janken has captured in their theory. So what am I wanting to do in this talk is basically talk about a pseudo-differential calculus with coefficients in a Hilbert-Cister module E over a unital Cister algebra A, such that following this deformation phenomena which have been done by Van Arp and Janken. And what exactly is this pseudo-differential calculus by Mischenko and Fomenko is that it's a filtered algebra of operators filtered by Z such that they contain the differential operators. Every operator is pseudo-local. I'll tell you what that means in some point. And every elliptic operator would admit a parametrics or an inverse up to smooth error terms. Okay, so that's what I want to do. Okay, so let's get down to business. What is this Van Arp and Janken theory I'm talking about? So I would now consider rescaling operators as I had considered before, but now over a family of points on Rn about fixed points omega. And what is this scaling family? This is the main definition called scaling family. So this scaling family is a family of operators for every non-zero t, such that each such operator produces, what is going on? So each such operator produces another family of operators for every omega, such that this new family should extend to t equals to 0. The old family was not defined for t equals to 0. This new family should smoothly extend to t equals to 0, as we saw for the differential operator case. But now all of this tied up by one more thing called the scaling relation, which says that if I have one more action of the positive scalars on my new family here, such that that recovers my the operator on the lambda tth fiber up to a smooth error term and a constant which is signified by the order of this or the degree of the scaling family. Okay, and my operators at the t equals to 1 fiber will be the operators which are our pseudo differential operators, and in this talk I'll be calling them as scalable operators. Okay, so let me give you a picture about what kind of operators am I considering here. So if I consider my operator as a distribution on Rn times Rn, then my operator should have support something like this, like transversely to the diagonal. This should be finite in extent. Now the rescaling business happens miraculously. What it does is that it shrinks this support more towards the diagonal. So if I consider the first operator minus the second operator, the scaling relation should tell me that it is given by some kind of smoothing business, right? So outside this diagonal, you kind of get a feel that these operators are very well behaved. So more formally, what I want to say that if you consider the scaling relation up there, and if you iterate it a few times, you kind of get a series on the right and one extra term. What you naively want to achieve here is that if you take the limit as m goes to infinity, you want the first term to vanish and you want to get a convergence sum as the second as part of the sum. This does not happen all the time, but in our situation of the off diagonal point in our previous picture, this is literally the expression of the operator. So what this tells you, the singular support of the operator only lies on the diagonal, and that makes this operator pseudo-local. Okay. Now a few highlights of this Van Arp and Janken theory, and we'll be assuming only compactly supported scalable operators here. And if I have compactly supported operators, it says that every negative order operator should be compact, and every order 0 operator should be bounded. By compact and bounded, I mean that they should extend to compact and bounded operators respectively on my L2 space of functions. Okay. And all in all, I get a short exact sequence of C star algebras which kind of beautifully sums up the entire theory, which is that if I consider psi star as the C star completion of my order 0 operators, what I'll have is a short exact sequence, but the first term comes from the completion of the negative order operators, the second term comes from the completion of the order 0 operators, the third term is kind of like a principal symbol what you naively have in the classical theory. Okay, so that's the entire gist of what I am talking about here. Okay, so what is my setup? My setup is I'm considering a unital C star algebra A, and I'm considering a finitely generated projective right A module, and I'm considering the exact same definition, but my functions are now E valued, or this projective module valued functions, and my operators are now right A linear operators. Everything remains exactly the same. Now, what about the highlights in this case? What we have checked and shown is that if you appropriately interpret your correct spaces and correct operators and your correct results, as in the Van Erp and Janken theory, everything follows, but you need to appropriately interpret what you mean by the terms. And all in all, to sum that up, you get a short exact sequence exactly like you had in the previous thing, where now your principal symbol functions will be like operator valued principal symbol functions, and you have like compact operators, bounded adjointable operators in the Hilbert module sense. Okay. So what now in terms of how I had started my talk in terms of representation theory? Where does this put me in that line? So I want to consider this certain class of operators called bisingular or operators of tensor product type. These are operators on product manifolds, but the main thing is that if you have a pseudo differential operator, or let's say if you have two pseudo differential operators on two parts of your manifold, and if you tensor product them, they might not be pseudo differential. So what you want to do is you want to have distinct decay / growth, however you want to think about symbol functions in the distinct directions of your manifolds, and that will give you a Fourier integral type operator like you usually have in pseudo differential theory. Now the main point of all of this, how this ties up, is that these bisingular or operators of tensor product type induces principal symbol maps on each of these component manifolds, or the two manifolds you started with. It induces map on each of these two manifolds as operators on the other manifold. So it's like decomposes into operator valued operators. That's why we were like studying that Mischenko-Fomenko type of operators. And interesting question we want to ponder here is that the initial order 0 C star algebra operators we were considering on the symmetric space, we want to replace that by these 0, 0 bisingular operators on the symmetric space, or for this group G equals to SL2R, that will kind of give me operators on SL2R times SL2R, or the symmetric space of SL2R times SL2R. The goal of this to classify this algebra in terms of representation theory, and also tie it up with the Van Erp and Janken theory, so that we can get a new kind of symbol or behavior with respect to some kind of tangent groupoid and stuff like that, such that maybe if we are lucky we can tweak that symbol and get something out for SL3R and maybe for higher real rank groups. Thank you so much.